Hello and welcome to another edition of James and Chris Science Videos, where today we're going to be looking at how to measure the rate of photosynthesis in different experiments. So I want to start off first of all with a recap, and the recap is what we did in the last video on photosynthesis, where we looked at the equation and we looked at the reactants and we looked at the products. So we start with the reactants, the thing the plant needs for photosynthesis to happen, the substances that it must get. And we talked about how carbon dioxide comes in from the air and how water comes from the roots, and they are the building blocks needed to react together with chlorophyll, not with chlorophyll, but with the aid of chlorophyll and sunlight in order to make glucose and leave the waste product of oxygen. So the purpose of today's lesson is not to go over that particularly, but it's to work out how I know what the rate of photosynthesis is and how I can measure that. So first things first, what is a rate? Well, in this case, the rate of photosynthesis is how fast it's working, how fast it's occurring. And to do this, we can use the products to measure it. In this example, we're going to try and use the oxygen to measure how fast photosynthesis is happening. The method we're going to use is called the bubble method. We're going to use bubbles in order to describe the speed of photosynthesis. So what I'm going to do now, we're going to go to the lab, and Mr. Kipax is going to explain to you today how the bubble method works.
Okay, what we're going to look at now is an experiment that looks at how a plant produces the gases from photosynthesis and the effect of light on the rate of photosynthesis. If you look very, very carefully down here, what we've raided Bob's pond, and we've managed to find some pondweed, which is a particularly good plant for this experiment when we want to look at how quickly photosynthesis actually happens. So we've taken some pondweed, we've put a filter funnel, a glass filter funnel right on top of it here, submerged it underwater, and then we've put a strong light source by the side of it. This light source gives the plant the energy it needs to power through the photosynthesis equation. And very carefully up the tube, you may be able to see every now and then there are some bubbles of gas coming up and out of the experiment. And this shows us that this plant is actively photosynthesizing. You can see the bubbles, which must be oxygen being produced by that reaction. Now, at that point, that's a nice little experiment that shows us that we've got photosynthesis coming up. In fact, as I look now, there's quite a few bubbles coming up. What we can use this experiment to do then is to actually look at how light and how powerful that light is, how that will affect the rate that this plant is able to photosynthesize. At this distance, we'd expect quite a good rate because we're nice and close to the light source. And we can then use a simple experiment, a simple technique, to see not only the number of bubbles. If we wanted to, we could count the bubbles coming up through the tube, but we can also use a measuring cylinder full of water and use the displacement of water as a way of measuring how quickly or how much oxygen is produced over a period of time. So we take this tiny measuring cylinder full of water, and this is the part of the experiment that sometimes goes wrong, but it's quite a lot of fun. Put your finger on top or thumb on top. I'm going to use my thumb, and then you need to invert this into the water and place it over the top of the tube. Now, if you've got that right, then the measuring cylinder will still have the water in it, and you'll be able to see the bubbles come up, and bubbles of oxygen will push the water out over time. So I'm going to do several takes on this one. You never know, it might be done in one take. I don't think I've ever done it in one take before. If we take the water, the measuring cylinder, we're going to put it up like so, and there we go. You can see that the water inside the measuring tube is still there. We get a little bit of dribbling at the bottom, and then we're just going to carefully pop the end of the filter funnel inside the tube. Now if I hold that, you should be able to pick up. You can see that as this plant is photosynthesizing, little bubbles are coming up, and we can then turn the scale on the measuring cylinder across, and we can actually over time be able to measure how much gas that plant has produced over a set period of time. So I can actually just let go of it now and just balance it, and there we go. Now, it is quite slow due to the time of year, even though we've got a strong light source on it, but you can see every now and then a bubble of gas will come up. Now, if you left that for, I don't know, 2, 5, 10 minutes, something like that, depending on how much photosynthesis is going on, you'd be able to tell the rate and how quickly it's displaced the water. So for example, if you left it for half an hour and you'd had 5 mils of water displaced from here, then you'd be able to say that this plant is producing 5 mils of oxygen in that particular period of time. A nice, easy, simple way of not only seeing photosynthesis, but also measuring the rate.
I tell you what, Mr. Kibak, shall we leave it for half an hour and see what happens?
I think we should leave it for half an hour and see what happens. It is going quite slowly, and if we can find a way of balancing it nice and carefully, in fact, if I just drop it to the side, it may even sit there. There we go. Right, so we're going to leave that for, well, let's have a look. It's on, what do we say, about 1 mil down? Yeah. We're going to leave that one for a few minutes, and then we're going to see how much gas was displaced. Right, Mr. Hardy and myself have been sampling the likes of lunch. While we've been away, this plant has been creating the next part of our lunch by photosynthesizing away, making lots of starch, and producing loads and loads and loads of oxygen. So we look very careful at the scale. It's been an hour, and we can see that over this period of the hour, we were about 1 mil down earlier, and we have dropped down all the way to, what's that, about 9, Mr. Hardy?
I'd say about 9.
9 mils. So we can say
9.5.
9.5, I like accuracy. 9.5 cm cubed of oxygen have been produced over that hour. So we can say that under this light intensity, we're getting a good rate, about 9.5 cm cubed of oxygen in 1 hour. Nice experiment. But what's the next step? Well, the next step is to repeat the experiment. And what we need to do is take our plant and we're just going to move it further away from the light source. And you may already be sitting there thinking, I can predict what this experiment will tell you. But let's see if our predictions are correct. We'll move the plant from the 10 centimetre line in the middle, and we're going to pull it all the way down, nice and carefully, down to 20 centimetres. So now we've doubled the distance between the light source and the experiment. We're going to take our measuring cylinder, just going to refill it. Thumb over the top as well and see how much mess we can make. Pop it under, and there we go. Right, making a lovely mess of the bench, but if we just pop it back over again. So, this time, the measuring cylinder's all the way up to the top. The plant is getting a light source, and perhaps not as strong, and if you carefully look, there should be 1 or 2 bubbles of gas still produced by the plant. So Mr. Hardy and I are off for a lovely cup of coffee and probably some
donuts.
Donuts. I like custard donuts, remember everybody? I know. Mr. Hardy prefers jam. Odd person. Custard all the way. Right, custard donuts. See you in an hour. Oh, right. Custard donuts. It was gone an hour. It's amazing how many custard donuts you can eat in 1 hour. New Guinness World Record there. Thank you very much. More importantly, our plant has been off and continued to photosynthesize in our absence and has produced some oxygen gas. If we look at the result after an hour, how much gas has been produced, Mr. Hardy? I can't read that one.
That's 6.
So 6 cm cubed of oxygen produced by our plant. Last time, at 10 centimetres, we got 9.5 cm cubed. This time we're down to 6. And that should be no great surprise that as you've reduced the strength of the light, then the effect has been less bubbles produced. Now, what we're going to do is we're going to give you a set of data that you will put into a table and then draw a graph of the results. So we'll give you the distance that the plant was held from the light, 10 centimetres, 20 centimetres, 30, 40, etc. And then the total volume of oxygen that was produced by that plant over that period of time. And then we want you to put that one into a graph of the results. And basically you'll be able to see from that graph what happens to the rate of photosynthesis as you move it further and further and further away from a light source. I think that's probably time for chocolate biscuits.
Thank you, Mr. Kibak. So I have the results for you. And you can see on the screen here are the results. So we've got the distance from the lamp, and then we've got the oxygen collected in 1 hour. Now, deliberately, I've put in an outlier, an anomaly. a result that is wrong. And so if you look over those results, hopefully it's quite easy to spot the result that is an outlier. When we get an outlier, what do? Well, we would circle it, and certainly when we come to draw our graph, we would ignore it in the drawing of the graph. So what I want you to do now is to take that data, and I want you to draw a graph for that data. Once you've done that, there's a couple of things I'd like you to try and explain. First of all, I'd like you to try and explain the pattern. And it's one of those, I've put it at the bottom of the graph, where they say in the exam, describe and explain your graph. And usually 2 marks, sometimes 4 marks, depending on the difficulty of the graph. If you want to get the marks, you need to have a sentence for both. A description is going to tell me whether the graph is going up or down, steeply, flatly, whether it curves, whether it doesn't curve. That is going to be my description. My explanation tries to explain why. And so this would be the further away from the lamp, and then you explain what's happening. That would be a description. This is because, there would be my explanation. And so you've got the 2 bits linked to it. Now, you'll notice that the graph itself gets to a point, and I think it's 50 centimetres and beyond, where there isn't any change, and it stays the same. And I want you to think for a second, why do you think that is? Why do you think that if I move it beyond 50 centimetres, the rate of photosynthesis stays the same? So I'm going to give you just a couple of seconds to think about it, and then we'll go through the answer. So, well, the answer is the lamp here, and the further you get away, actually, the less effect it had. But now, the light from elsewhere is affecting the rate of respiration, and photosynthesis. So as soon as you go beyond the influence of the lamp, you're now into the influence of all the lights in the lab, all of the sunlight that comes in, and that's going to be driving the rate of photosynthesis, not the lamp. So let's summarise. We can use aquatic plants like pondweed. This is a type of pondweed called hello dear, which sounds like an old lady saying hello. Hello dear. Otherwise known as Canadian pondweed. That is really useful for us because as an underwater plant, when it produces oxygen, it produces them in the form of bubbles, and we can measure those bubbles. We've learnt that the more intense the light, the closer you got to the light, the higher the rate of photosynthesis. That's hopefully not surprising to you. More light, more photosynthesis. And I've put that Mr. Kibak's preferred custard, and that's clearly crazy, so therefore we can now discount most of what he says. Thank you very much for watching. Hope to see you again soon. Bye-bye.